the Linford live stream. We are going to be going over a couple topics today. In particular, we are going to be reviewing sections 10.1 and 10.3 as we did this morning, as well as section 10.4. But beyond that, we're also going to try to explore some section of 10.5, what you should have been working on today, and hopefully answering any questions people have. If you would like to leave a comment, ask a question, feel free to go ahead and drop that question or comment into the live chat that we have going on. So let's start with sections 10.1 and 10.3. This should be a review of what we did on Monday. And as we go and explore this topic, what we want to do is we want to make sure we're solid on both methods of how to go about simplifying radical expressions. So the first thing that I'm going to do is look at problem 2 from the independent practice, and that is the square root of 72x cubed. So a couple ways of going about doing this. We can either first think about what are the factors of 72, and what are these factors that go and or which of these factors go and help to break down square roots. In other words, which of these factors are in fact perfect squares? Let's see if I can get my stylus to connect. Okay. Well, one in fact that I know is the square root of 9 times the square root of 8 is the same thing as the square root of 72. So I can break it up into those factors. And 9 can break down into 3, but then the square root of 8 can also break down into the square root of 4, and the square root of 2. Now the square root of x cubed can break down into square root of x squared and the square root of x. Hey, looks like we got some listeners. Happy to see you. Let me know if you have any questions or any comments. So, as we keep breaking this down, we can take the square root of 2, or the square root of 4 into 2, square root of x squared into x, and we're left with the square root of 2x. So our final answer should be 6x root 2x. Now, remember that we also have other methods for going about doing this, including the prime factorization. So in this problem, I'm going to go and break down the 16, the x to the 5th, and the y to the 4th into all of its prime or most basic factors. So if I took 16, we can break that into 2 and 8. 8 can go into 2 and 4, and 4 can break down into 2 and 2. So 16 is basically 2 to the 4th power. So we can rewrite 16 as 2 times 2 times 2 times 2, the cube root of that. And then we can break up x to the 5th as x times x times x times x times x. And y, let me clear some space here. Y, we're going to do the same thing. We're going to list it in expanded form. The cube root of y times y times y times y. Then we said we need to go and make groups of however much the index was. So if the index is 3, we need to make groups of 3. And it looks like in each of these we have at least one group of 3 of the terms. So let's go ahead and make those groups. Let's see, the cube root of 2 cubed, and we're left with just 1 2 by itself. We can also take the cube root of x cubed with only 2 x's left to themselves. And then we can take the cube root of y cubed with just 1 y left to itself. As we go about simplifying this, let's see, 2 cubed, and the cube root of that is just 2. The cube root of x cubed is just x. And the cube root of y cubed is just y. And the rest of these are just kind of left by themselves in the radicand. So the final answer should be 2xy times the cube root of 2x squared y. If there's any questions on this, let me know. We're having the live chat go on. Let me know if there's any questions or things that you want me to go over in particular, okay? Or if I'm going a little too fast. One thing I want to point out that I pointed out in this morning's live stream is that you want to be careful with your writing and always make sure that you include a little bit of a space in between the values outside of the radicand and the radicand itself. The reason for that is sometimes students might write this as 2xy cube root 2x squared y. And when they put that 3 there, they're not sure, is that a y cubed or is that a y times the cube root? In Microsoft Word, it's actually very difficult when typing this to kind of distinguish that. So oftentimes on your homework and exit tickets, I try to put a couple spaces in between there so you can see. But in your writing, try to make sure you always include a little bit of a space there, just so it's a little easier for you to see. Oftentimes I'll see students, if they have a little bit of messy writing and they cram it all together, sometimes as they're working through, they would think a cube root is a cubed value, and they'll leave it as that. So that can mess up your problem, so just be a little careful with that. Now let's get into yesterday's work of section 10.4, actually going about adding and subtracting radicals. So one of the things we said is you can always add radicals if they have like radicals. And what did we mean by like radicals? Well, like radicals are radicals that have the same index and the same radicand. I would blame my handwriting on the poor stylus, but let's be honest, it's just my handwriting. So, like radicals have to have the same index and the same radicand. Now, I saw people on yesterday's exit ticket look at a problem like this and say, oh, it can't be combined because 18, 27, and 50 are all different values. So you actually can't go and simplify, or you can't go and combine these radical signs together, and you can't add them together because they're not like. But definitely make sure before you make a statement like that, pause and think about it. We want to see, sure, these numbers are different, but can they be simplified down to get the same value? And in fact, yesterday's exit ticket, they could be simplified down. So let's try to break them down one by one. I like to do this in separate colors, and I like to do this kind of on some side work. So I'm going to break down 18 in red. I'll do 27 in blue, and I'll use green for 50. So I'll break these down separately. I just find it a little more organized in our work, especially when you get to those more lengthy problems. So the square root of 18, well, that's pretty simple. That's just the square root of 9 and the square root of 2. And that can break down into 3 root 2. Let's take the square root of 27. That's the square root of 9 and the square root of 3. Yes. So that can break down into 3 root 3. And then let's break down the square root of 50. That can break down into the square root of 25 and the square root of 2, which is 5 root 2. So let's go ahead and plug these in. I liked having all this work to the side as opposed to just trying to cram it all together in one string of text, just because your work's going to get kind of messy. So we have 5 times 3 root 2. And then we're going to add on, let's see, that was in blue, 3 root 3. And then we have 4 times 5 root 2. All right, so with all of these subbed in, we can start simplifying this down to 15 root 2 plus 3 root 3 minus 20 root 2. Now we can go and see, are there any like radicals here? And you should notice that, yep, there are 2 like radicals. They have the same index, they're both square roots, and they have the same radicands. So we can combine those. 15 root 2, take away 20 root 2 is negative 5 root 2. And then 3 root 3 doesn't really combine with anything, but that's okay. Doesn't always have to. Brennan, no, we're not doing any trig right now. Sorry to disappoint. Now, let's go ahead, if there are no questions, and let's move on to a much more complicated problem. But in reality, this isn't too complicated. The big thing with simplifying radicals, especially when you have to combine multiple radicals, is going and working in as organized as you can. Keeping your work structured, organized, using colored pencils and scratch paper, that's going to help out is essentially with 90% of the work. So I'm going to break this down. I'll do this part in red, this part in green. Why does technology not like me? All right, looks like we're back. All right, first up, let's go ahead and let's break down the the cube root of 64x to the 5th y squared. So let's do that to the side here, the cube root of 64x to the 5th y squared. Now, 64 can break down, so let's do some work to the side. 64 breaks down into 4 and 16. And 16 breaks down into 4 and 4. 4 is 2 and 2, that's 2 and 2, and that is 2 and 2. So let's see here, 1, 2, 3, 4, 5, 6. 2 to the 6th power is 64. So we're going to take the cube root of 2 to the 6th power. We'll take the cube root of x to the 5th. And we'll take the cube root of y squared. Let me get some space over here. Now, and if you have any questions about any work that I erase, feel free to let me know. We're going to be posting this video afterwards so people can go back and check through any of the questions that we went over and review any of the problems. And yes, I am streaming with OBS. I am on that level. All right, now, if we take the cube root of 2 to the 6th power, we could structure this all by putting an expanded form and making groups of 3, but I think it's pretty obvious for us that there are 2 groups of 3s here. So we can take the cube root of 2 cubed and the cube root of 2 cubed again. Now for x to the 5th, we can say, well, let's take the cube root of 3 of the x's, and then we'll take the cube root of 2 of the x's. Now when it comes to y squared, the cube root of y squared, we don't really have 3 y's to structure together, so we don't expect that part to simplify down at all. All right, now let's try to go ahead and simplify each one of these. The cube root of 2 cubed is just going to be 2. The cube root of 2 cubed again is just going to be a 2. The cube root of x cubed is just x. And then the cube root of x squared, that part doesn't break down, and neither does y squared. But that's okay, we don't expect it to. When your exponent is less than your index, you're not likely to break down at all, or you're not going to break down at all and simplify the radical. So our final answer here should be 4x times the cube root of x squared, y squared. So that's what this part is. Let me write it up here, just so we don't forget it. And let's go ahead and clear our work, and let's start simplifying the next problem. Hey, Math Club is going well. Thanks for asking. Stop by and visit sometime. Fourth grade math. Weren't you just asking about trigonometry a minute ago? All right, let's get back to the cube root of x squared, y squared. Now, automatically, we should pause and think about this for a second, that this isn't going to factor down at all, or it's not going to simplify down, because even if we broke it up into the cube root of x squared and the cube root of y squared, we can right away see we don't have 3 x's, or more than 3 x's, to group together. So these aren't really going to simplify down at all. Instead, we're just going to have to leave that radical as it is. But let's take a look at the third one, the cube root of x to the 8th y squared. Again, I can expect x to the 8th to break down because there's a couple groups of 3's in there, but y squared doesn't seem like it's going to break down at all. So the cube root x to the 8th, y squared. Well, let's take 3 of the x's, and I can take 3 more x's, so there's 6 x's I've used up. And then let's just take the last 2. And then the same thing with y squared. So the cube root of x cubed simplifies to x. Cube root of x cubed simplifies to x again. And then the rest of the stuff really doesn't break down. So we're left with the cube root of x squared, y squared. So here is our final answer for this radical, simplifying this one. We have an x squared, and we have the cube root of x squared, y squared. Ooh, looks like I ran out of room. Let's see if I can rewrite that. Okay, let me go ahead and clear some space here, and let's go about simplifying and combining all of these radicals. Because that's the big part of our problem, is so many times I see students do all of this amazing work and then they stop. They forget that we actually have to go and simplify all of this stuff down. So let's go ahead and start substituting these values in. We have x times, let me change up colors here so we can see what we're doing, 4x cube root of x squared, y squared, minus x squared, and, well, this part didn't break down, the cube root of x squared, y squared. But then the next part, let me write down here, plus 5 times, this radical broke down into x squared and the cube root of x squared, y squared. And then, let's start simplifying everything. 4x squared, cube root of x squared, y squared, minus the x squared and the cube root of x squared, y squared, plus 5 x squared and the cube root of x squared, y squared. Now, we've broken everything down, and we can go ahead and see right away, yes, we do have like radicals here. They have the same indices, 3, the same index, and they have the same radicands. But before we go and actually start combining things, we have to make sure that the things we're going to add and subtract together are in fact like terms. For example, when we combine like radicals, we're just really adding the, I call them like the pseudo coefficients on the outside of the radical sign. So before you go and add those together, make sure they're actually like terms and you can add them together. So we have 4x squared minus an x squared plus 5x squared. Good news for us, those are all like terms, so we can add them together. Will they always be like terms? No. Be on the lookout for that, okay? Especially, I think, in the advanced practice. So 4x squared minus x squared is 3x squared. 3 plus the 5x squared makes 8x squared. And then we have the cube root of x squared, y squared. That is going to be our final answer for the entire problem. All right. Now, before we get to the next problem, keep in mind that I am running the live chat on the side for questions and comments about the mathematics that we're going over. Treat it just like you are in class. So make sure that your comments relate to what we're going over. Thank you very much. Now, let's explore this next problem as we get into what today's lesson was all about, and that is how to go about multiplying radical expressions. Now, as we go and begin multiplying these quantities, we want to remind ourselves that they are very similar to when we multiplied polynomials together. Because, again, this multiplication is all really distribution. It's just a breakdown of distribution, so we're going to distribute each term through individually. And if you remember, I am not the biggest fan of distribution or that dreaded term FOIL. Instead, I really like the box method. And you'd probably notice on the homework key that I use the box method quite frequently with this. So rather than go through and distribute each thing through individually, let's set it up so we have the box technique. So I'm going to take 8 and the square root of 7 and negative square root 5. And let's go ahead and multiply that through to the square root of 7 and 3 root 5. Now, this again is working very similar to what we did previously, right? Where we're just distributing each term through individually. But instead, it gives us a really nice visual way of going about doing this. Should we use the FOIL method? We could, but I don't know. Sometimes when you use the FOIL method with these problems, I could try one out and see. It gets kind of messy, right? When you have this long string of radicals all together. Usually when students see things all kind of worked out horizontally, there's a lot of information there as opposed to the box method that, kind of structures it a little better, I'd say. But you could definitely go ahead and use FOIL with this. But I'm going to try the box method. Before I go and actually start simplifying, I'm just going to do straight multiplication. So 8 root 7 times root 7. We know that when we multiply radicals together, we're going to multiply the radicands on the inside. So root 7 times root 7 is root 49. And then when we have 8 root 7 times 3 root 7, we're actually going to do a couple things. We're going to multiply the numbers on the outside, and then we also multiply the radicands on the inside together. So 3 times 8 is 24, and then root 7 times root 5 is root 35. Let's take a look at the similar problem for negative root 5 times root 7. Negative times a positive is a negative. Root 5 times root 7 is root 35. And then the very last spot, we have 3 times a negative is negative 3. Root 5 times root 5 is root 25. Now, when we go and have all this multiplication together, we can actually start simplifying things down. Expect that when you multiply radicals, the values are going to break down. So don't just leave them there, because most likely you've multiplied by a number so big that a cube root or a square root factor can go into it. So let's clear up some space here. Instead of 8 times the square root of 49, we know that is just a 7. And 7 times 8, anyone? And then the live chat falls silent. All right, 56. All right, now let's take a look here. Root 35, that doesn't really factor down because the prime factors of that are 5 and 7. So I'm not going to simplify that or this one, but we can simplify the square root of 25. That's just going to be a 5. So 5 times negative 3 is just going to be negative 15. What I love about the box method, you can see right here, like terms are on the diagonal from each other. They're right there and right there. So we can go ahead and combine those like terms. We have 56 minus 15. Let's see, 56 minus 10 is a 46. Minus 5 is 41. And then we have 24 root 5. Take away a root 5 should be 23 root 5. I'm sorry, root 35. And there we go. That should be our final answer. Are there any questions about this problem? I see we have a little bit of a delay going on. Let me know if it gets caught up. Got it. Looks like there's a bit of a delay, so I'll wait for, I'll try to wait, I think sometimes OBS has about a 20-second delay. So let's work with this a little bit. Let's see if it works. All right. let's go ahead and try another problem, this time a little more expanded. So here, FOIL isn't really going to work for you because FOIL only works when you're multiplying two binomials together, or you can think of it like two groups of two terms. So in this case, you could do the distribution method. And if you wanted to do that, you would have to distribute each of these through individually to each of these terms. That's going to be a little elaborate. I'll show you what it looks like, and then we'll test the box method to see if it's any clearer in the writing. So let's see, we would have to distribute 3 root x to root x, and then 3 root x to root xy. Oh, actually that's a subtraction. So 3 root x to negative root y. Then we have to distribute all of 2 root y through. So let's do 2 root y to root x plus 2 root y to root xy minus 2 root y to root y. Not too bad, but I don't know, gets kind of messy. 10i. Oh, this is the problem 10 from the independent practice. So Kevin, yeah, this is independent practice homework that I'm doing, problem 10. All right, let's go ahead and we can start combining these things. We get 3 root x times root x is just x, plus 3 times, all right, root x times root x is x, and the root y is left there, minus 3 root x root y is just root xy, plus 2, we still have another root xy, plus 2, okay, the root y's combined together to make a y, and we're left with a root x, minus 2, root y times root y is y. All right, we can go ahead and try to find the like terms now. Let me see if I can circle those in blue. It looks like the like terms are right here and right here. And that's pretty much it. It's just those two. So our final answer should be, if we combine those, 3x plus 3x root y minus 1 root xy plus 2y root x minus 2y. This is not too bad of a problem, I guess, but I don't know. When I see things all strung out together and we're trying to do it part by part, but kind of all as one piece, it just seems kind of messy. And a lot of times students will struggle at this section where they have to try to find the like terms. I'm going to try to do this again, but this time with box method, just so we can see the structure to it and how it kind of fits a little nicer in these problems. All right, if I set up the box, I'm going to have 3 root x and 2 root y. And over here, I'm going to have root x, root xy, and root y. I'm going to move a bit faster through this, so let me know if you have any questions. 3 root x times root x is 3x. 3 root x times root xy, well, the root x's combined together, so we have 3x root y. 3 root x and root y, and nothing simplifies there, so we're left with the xy in the root. And then the same thing for here, we get 2 root xy. Now in the next problem we have 2 root y times root xy. Now those y's are going to combine so they can come out of the radical, and we're left with 2y root x. And then the very last problem, the root y's combine to just make a y. Are there any questions on any of this? I'm going to wait a couple, about, I think we said 30 seconds. I'll wait about 20-30 seconds. Let me know if there's any confusion on any of these problems. think it's been about 30 seconds. Either the delay is longer or you have no questions. I'm going to guess you have no questions, so we can just move on. All good here. All right, sounds good. So, what I like about this box method is we can really look on the diagonals for these like terms. We notice that there's not really going to be any right here, which is fine, but we do have some on this diagonal. Okay? So we have the 3 root xy and the 2 root xy. So if we combine these like terms together, let's see what we get, which should be the same as before. We have a 3x plus a 3x root y plus, anyone catch the mistake? I'm going to pause a minute. I'm going to wait to see if anyone sees it. I'm also counting to see how long this delay is. So let's take a look. What's the issue here? Because this isn't matching with the last problem. So let's see, what could that mistake be? Why is the 3 root xy and the 2 root xy not combining like the last problem? We didn't have a 5 root xy in the last problem, or this problem we did before. So what do you think that mistake is going to be? I'm going to wait till I see it in the live chat. You can blame the delay, but I wonder if some people are frantically trying to figure out. There are more like terms? Nope, we still just have the 2 like terms. We have the 3 root xy and the 2 root xy. Those are really the only like radicals we have here. So we can't combine anything else. So what could it be? Because we didn't have a 5 root xy before. And we're doing the same thing here. We're just doing box method. Box method is distribution. It's just we distribute one thing through in one row and one thing through in the other row. So take a look at that setup. Always double check. If something's not going right, start with the setup. See if there's any mistakes. This live chat was so talkative. Then I'm like, uh-oh, what's wrong with the problem? And then people fall silent. Let's think. Because there wasn't a 5 root xy. And these are still the only like terms that we have, so we should be able to combine them. Okay. We're all thinking. All right. Hint, Kevin. Look at the setup. Always double check before you get too lost in all of the work. See if there's a setup issue. Ah, there we go. It's a negative square root y at the top. So, that was a problem. Didn't look at the sign there. It's got to be a negative. So, let's just go ahead and adjust that. That should be a negative root 3y, and this should be a negative 2y. Well done, Kevin. All right, now, let's go ahead and combine these like terms so we end up with negative 3 root xy and positive 2 root xy becomes negative root xy. Then we still have the positive 2y root x, and this time a minus 2y. So we should be set with everything here. This is how we're going to go about multiplying these radical expressions together. Now, oftentimes students get this and they're like, oh gosh, this can't be the answer. No, it's totally fine. Remember when we were multiplying polynomials and we ended up with an even larger polynomial? That's fine. Expect that to happen. Double check though, right? When you're going through and multiplying, we expect that some of these radicals will simplify down into whole numbers or single term variables. So don't be, too afraid with your answer simplifying down or ending up with a large expression like this. That's totally normal, and it should remind us of when we go about multiplying polynomials. Ah, geez. I was very optimistic when I wrote this problem down. Now I'm looking at it like, oh, gosh. When the teacher's so lazy, he doesn't even want to do his own problem. All right, let's go ahead and give it a try. We're going to box method this. If you like to do the distribution method, go for it. Just, be careful with when you're distributing. The best thing you can do for distribution method is to write everything out. Use parentheses, write things down. All right, let's take 2 and the cube root of 3x, and let's take negative cube root of 2x, and let's put these as the columns: 4 cube root 9x to the 4th, a 7, and a negative 6 cube root 12. Kevin, notice that I'm using the negative here, so we should be good this time. All right. I'm going to, a lot of times when students do this multiplication, they try to multiply things together in their head and simplify things in their head and just write the simplified answer down. You'll notice in the videos, I don't do that right away. I just go ahead and multiply the things together because sometimes it gets to be a lot when you're going and actually multiplying down these things and simplifying them down. So try to be a little careful. I always recommend the more steps you do, the less likely you are to make a small error. The more you're seeing all this work drawn out. So let's multiply the things on the outside. 2 and 4 make 8. And let's multiply the things on the inside. We have the cube root of 27 x to the 5th. Now let's multiply the 7 and the 2 to get 14. And then we have the cube root of 3x. We can multiply the things on the outside, and we get negative 12, and the cube root of 3 times 12 is 36, x. And then let's move to the next row. We have a negative and an 8 to make negative 8, and then we have the cube root of, oh my gosh, I'm messing up. I'm trying to watch the live chat and also right at the same time. We have negative cube root 2x, and we got to multiply by the 4 cube root 9x to the 4th. So let's do that. The negative and the 4 make negative 4, and then we have the cube root of 9 and 2 make 18, x to the 5th. Negative and the 7 makes negative 7, and then we have the cube root of 2x. And then the double negatives make a positive 6, and the cube root of 24x. That's a terrible 4, but whatever. All right, now we've gone through and we've performed all this multiplication. We want to make sure that we're able to simplify things down. It's probably a good idea to have a separate section, right? As opposed to erasing our work, probably have a nice separate section, maybe another box to go and show how we're breaking each thing down. So let's start with one thing at a time, and let's simplify down 8 cube root 27x to the 5th. Let's see, that's 8, and the cube root of 27. 27 is actually a perfect cube, if you remember. It's 3 times 3 times 3. So maybe we can skip ahead and just say that's a 3. And now let's work on the cube root of x to the 5th. Well, we can group 3 of the x's together in the one spot and 2 x's together in the other. So we end up with 24. The cube root of x cubed simplifies to an x. and the cube root of x squared just stays the same. Let me see if I can clear some space here, and we'll rewrite this simplified version in its place. So we have a 24x cube root of x squared. Now, we can go through and we can quickly check the next few. For example, 14 and the cube root of 3x. 3 is a prime number. It's not going to factor down. And same thing with x, so it's not going to have a cube root. So that's going to stay as it is. Same thing with the cube root of 2x. That's not going to break down at all. So we'll leave those as they are. The next things to check are things like the 18, the 36, and the 24. I think I'm going to start probably with the 36x in the far right. So let's do negative 12 and the cube root of 36x. Well, 36. 36 can break down into 2 and 18. 18 is 2 and 9. And that's 3 and 3. Well, do I see 3 pairs of anything here? No, I just see a pair of 2s and a pair of 3s. I don't see a grouping of 3 at all. So if I were to try to make a cube root, I'd only have 2 of each of these numbers. So it doesn't seem like the cube root of 36 really can simplify because its prime factors are 2 times 2 and 3 times 3. So actually, we're going to have to leave that as is. So that's not going to break down any further. Now let's take a look at 18. Well, we just kind of broke down 18 into 2 times 3 times 3, right? It's 2 and 9. Well, those really aren't any groupings of 3 either. We have 2 3s and 1 2. Yeah, that's not going to simplify. So this is as simplified as we can get it, the cube root of 18 and x to the 5th. Well, we could break down the x to the 5th, I guess. So let's give that a try. We have negative 4, cube root of 18x to the 5th. We could leave that as negative 4, cube root of 18. And then the cube root of x cubed and the cube root of x squared. This will simplify to negative 4x and the cube root of 18x squared. So I guess we could go and pull out the variable. So let's be careful with that and make sure we get all this fully simplified. So let me erase this and let's put the simplified version in its place. Negative 4x cube root of 18x squared. Also, if you can't read any of my handwriting, just let me know. I know it seems my poor handwriting gets compoundedly worse. Is that a word? Compoundedly? Probably not. But it gets much and much more worse as I write on a tablet with a stylus. And then the last thing to break down is 24, the cube root of 24. So let's try 6 cube root of 24 and an x. Well, 24 can break down into 2 and 12. 12 can break down into 2 and 6. And 6 can be broken down into 2 and 3. And what do you know? I got 3 pairs of 2s there. All right. So we have 6 and the cube root of 2 cubed, and the cube root of 3, and the cube root of x. So we can break down the cube root of 2 cubed into 2. So we have 6 times 2. And the cube root of 3 and the cube root of x just come back together. So we end up with 12 cube root of 3x. And there we go. We've gone through and we've simplified each of the multiples that we got. But now, just to be careful, we need to actually combine all of these, or at least write them as a sum. Write them all being added together. In fact, can any of these combine? Let's see if there's any like terms. There's a root x squared, a 3x, an 18x squared, oh, a 3x, so maybe these can combine, but otherwise we have a 2x and a 36x. So it looks like there's only one combination of like radicals, and those are these two values. So let's take 24x and the cube root of x squared. Let's add on, well, I guess we can combine these like terms together. 14 and 12. 10 and 10 make 20. 4 and 2 make 6, so 26. Cube root of 3x. Minus 12, cube root of 36x. Minus 4x, cube root of 18x squared. And then minus 7, cube root of 2x. All right, this should be our final answer. We've gone through and we performed our multiplication. We simplified down each of the multiples, and then we looked to see if anything could combine. Always make sure that you're writing your answer as a sum. Don't just leave it in the box method. Make sure that we have it all written out as one thing added to the other, or subtracted, give or take. If there are no longer any questions, then I think we might bring the live stream to an end. Remember, if you have any questions, feel free to contact me at klinford, KLINFORD, at wccnet.edu. Let me know if you have any questions or want me to go over anything else. Also, feel free to schedule a meeting with me if you would like to talk more in depth about specific problems, or if you're having trouble with anything. You can schedule a meeting with me at my website, Linford Math, all one word, linfordmath.weebly.com. Under the Contact tab, you can go ahead and schedule a meeting with me through Google Calendar. So if you have any other questions, let me know. And until next time, this will be the end of our live stream. Take care.